Now, as we progress through today's program, we have among us our second chief guest, Dr. Deepak Kumar Mishra, sir. Sir is a retired professor of Electronics and Instrument Engineering Department of SGSITS. Sir has done his Master of Engineering in Applied Electronics and Servo Mechanism from DAVV Indore in 1984. And Sir has done his PhD from DAVV itself in 2000. Sir was working in ISRO Satellite Centers, Bangalore from 1981 to 1988 and in Space Applications Center in ISRO Ahmedabad from 1988 to 1990. After that, Sir was working in Professors of SGSITS Indore. Sir has life member of Institution of Engineering and life member of Institutions of Electronics and Telecommunications Engineer. His researches including electronics and instrumentations, VLSI technologies, and low power analog and mixed signal VLSI designs. Now I request Dr. Deepak Kumar Mishra sir to uphold the dice.
Thank you.
Thank you.
I should say good morning or good afternoon because time is 12 o'clock. Good morning only. Okay. I think you have listened to my introduction. I was professor and head in electronic instrumentation at SGSITS. Now I am retired. So I am not there anywhere. Okay. So actually, this particular subject I have tried to make it very interesting. It is not very lengthy or that thing. It is interesting, so I have chosen this particular subject. Okay, so I am going to talk about system on chip. Mostly, everybody is familiar with the system on chip. What is system on chip? See, if you see the progress in electronics, and recently VLSI has taken over the complete electronics part of that. So analog electronics, digital electronics, microcomputer, microprocessor. So if you make separate, I will take a particular slide that will show you that this is electronics, this is microelectronics, this is system on chip. Okay. Okay. So introduction. First, I'll take introduction. What is system on chip? System on chip. If you just how I'll let you. System on chip. Short form is SoC. Okay. So when I was a student in electronics at SGSITS, I have done my BE, MTech, PhD from GSITS. I have worked in ISRO also. So when I was a student, that slide will come that we used to make analog electronics, digital electronics. So some cards, PCB for analog electronics, some cards, PCB for digital electronics. Nowadays, analog electronics, digital electronics, microcomputer, microprocessor, things have come on single chip, silicon. So everything is there on system. Complete system is there on chip. So because of that, we call it system on chip. Okay. So these are all the headings you can say that which I will cover slowly. What is SoC? SoC characteristic. How SoC will work. How performance of SoC you can judge. Then benefits and drawbacks. Then what are all benefits of SoC? What are all drawbacks of SoC? That we'll see. SoC challenge. There are certain challenges. Still, VLSI is not free. VLSI has some challenges. How you are going to reduce the dimension? Already previous talk they have told that 18 nanometer, 20 nanometer. So where we will go? 18 nanometer, 10 nanometer, 9 nanometer. Then where we will go? That is a challenge nowadays. So VLSI has come to saturation. Now we are not able to reduce the dimension. Some 20 nanometer, 10 nanometer, how to go lower dimension. So there are challenges. So scientists, engineers throughout the world, they are working on that and they are finding alternative technology also for VLSI. Do you know the capability of VLSI? If you just go through a CPU of a computer, Pentium or other things, you will find millions of transistors on the silicon chip. Millions of transistors. Now, when you know that millions of transistors are coming on a chip, in that case, how that thing is possible? So that how possible means they are trying to reduce the dimension and dimension. So when you are putting millions of transistors interconnections, one transistor gate will be connected to some another transistor. So how that is possible? That is possible because of CAD tools, cadence, synapses, mental graphics, Xilinx, all those things. Today, millions of transistors we have to put, then in that case, gate length, gate dimensions, feature size, that we'll have to see. So, do you know Moore's law? Everybody are familiar Moore's law? Those who are just student of VLSI or student of electronics, they will know Moore's law. Moore's law, number of transistors, like millions of transistors are more than that transistors. Number of transistors are getting double and double in 18 months. Earlier, this was 2 years, but now it is 18 months. So Moore's law is still valid. You can't say that no, VLSI has started in 1970s, 1980s, but Moore's law is still possible. You can just notice that this previous, the graph was there, no? Okay. This graph, you can see that microprocessor, Intel microprocessor 4004, then 8080, 8088, 802, like this. The progress of electronics has taken place like this. So Moore's law is still valid. Number of transistors which we are trying to say that Pentium processor, so now so many advanced version of Pentium has come. So now you can't say that what will be the future, how many transistors will come. So limitation has come. So this much transistors will be there, and okay, the next slide. Okay, this is very important slide. This will give you idea that how to fabricate, how. Everybody is familiar with wafer. We say that wafer is the starting material for making integrated circuit. So how wafers are prepared? VLSI technology part. MGS, EGS. Have you heard of MGS, EGS? Those who have studied electronics, those who have studied VLSI technology. MGS, metallic grade silicon. So silicon we have to make for making integrated circuit, for making wafers. So silicon is available in some form. A huge amount of silicon is available. Sand, coal, all the wood, all those things. Okay. So first, the available raw silicon available will not be useful for making integrated circuit. We have to purify the silicon. We have to purify silicon. So that is a procedure. First silicon, we will heat, we will melt the silicon, and then liquid silicon, molten silicon is collected and it is solidified. So that is known as metallurgical grade silicon. Metallurgical grade silicon is not useful for making integrated circuit. Further, you will have to purify the silicon. So after purification, we make EGS, then from EGS, the starting thing is ingot. Ingot is starting some 1 meter size of length of the ingot, and some diameter is about 400 mm, 300 mm. And then from ingots are made slices, and that one slice will be the wafer, blank wafer, which is shown in second step. Ingot, wafers. And then after that, wafer will do processing of wafers. Wafers are clean, wafers are polished, then wafers are used to make integrated circuit. As in earlier lecture, he has told that wafers are available in a huge quantity in company. Metallurgical silicon we will purify and make electronic grade silicon, and from electronic grade silicon we will make wafers. After making wafers, we will have to do some fabrications. What we will do, I will come to that thing. So many steps are there. After purify the silicon, after making the wafers, pattern wafers. Generally, when you just consider a wafer, in that case, about 1,000 small chips are there. Dies are there, so 1,000 are that thing. And each die is going to just make same circuit. If we are making an operational amplifier on wafer, in that case, all silicon chips, all silicon dia, we call it dia. These square thing, these are wafers, square things, we have slices we have made and we have square things, and these things are nothing but dia. And suppose if you are making one IC, then all dia, same IC will be made. If you are making op-amp, same op-amp will be made on all dia. Okay, so after making dia pattern, this dia, you can just say that you make the circuit on dia, fabrication started. Okay, so first of all, oxidation will be done. Oxidation is done to prevent the wafer surface from contamination. Purpose of oxidation is this one. Okay, so now once oxidation is done and other processing is done, wafers are further sent to make dies. And after dies, bonding, input connection, output connection, input pin, output pin, so that dyeing is done, bonding is done, then after that metallic connections are done, and then chip to the customer, then wafers are given to the customer. So actually, there is no need for everybody to make wafers. Wafers are available from so many companies. So when you are starting a wheel size design, in that case, you can purchase the wafers from the market. Open market wafers are available. You need not have to purify MGS, EGS, because wafers are available. Okay, next slide. Okay, this is another slide. The small separated part is dies on which we are going to make the circuit. Next slide. Types of IC design, analog or digital. And these digital ICs are done full custom. Do you know full custom? Full custom is everything from scratch. Full custom. Every transistor designed and laid out by hand. Then next is ASIC. If you are not going for full custom, then application-specific integrated circuit. Application-specific integrated circuit means particular purpose is there for making that IC. Like microwave controller, washing machine controller, in that microcontrollers are used. So that is ASICs. ASICs means they will have some particular purpose. Microcomputers are used for making ASICs. Okay. So design synthesize automatically from a high level description. Like high level description like VHDL, Verilog, analog VHDL, analog Verilog. So all those things are done. So they are ASICs for particular purpose. Then semi-custom. Semi-custom means some things are available. Some already you have made particular design. And if your design is working and if your design is to be used later on, so you will make it an intellectual property, IP core. So you will just registered IP core. So always it is not necessary to do every design from scratch. Because if some design is already available and if that design is required by me, so what I will do, I will just see that in market whether such designs are available or not. If they are available, then I will pay the royalty, I will pay the cost, and then I will use that design and I will make further design. So this is semi-custom. Semi-custom is for something you will start from scratch, and something you are already available we will use and together we are going to make. It is not necessary always to spend time for making everything. Okay, next slide. Standard cells are pre-designed with the next slide. Full custom design. Every gate is carefully designed. As I told, you have to start from scratch. Everything you have to design. You will not use IP cores, other things in full custom design. Advantage of full custom design, high density. That is, if you are making some design 50,000 chips or 1 lakh chips, in that case, when you are doing a high density, in that case, this particular full custom design is useful. Disadvantage, high design time. If you are going to make everything from scratch, and if you have to make a 50,000 IC, in that case, you have to start from scratch, so it will take a lot of time. So that it will become cumbersome, because when millions of transistors are to be put on IC, In that case, and then connecting interconnections and other things. So every design will be cumbersome. So we'll have to use IP cores and other things. Okay, then that next. Okay, so feed through logic cell. Suppose if you are making some particular part as a memory, RAM, multiplier, so that part will be separate. And remaining things are already logic cells have been designed, their layout is available. In that case, we'll go for just routing, how to interconnect some logic cells, and from logic cells you will make more complex IC, and then in that case you have to just route the channel and you have to just interconnect, because everything is now available as a feed through logic cells. Next. Okay, same standard cells, they are available. So you just repeat and you will just do the connections and you will make that. So next slide. This slide, device circuit topology. If you want to make a IC, then topology is device. If circuit has got some repeated things, so we'll make this we'll do the topology. Size transistors. Then when millions of transistors are there, millions of CMOS transistors are there. In that case, we will just size transistors. If particular transistors, higher versions are available, then we will use those transistors. Simulations. Okay. When millions of transistors you are putting on IC, so it is not possible for you to test complete million transistors, and then interconnect them and then make the other part of that complex things. So you have to go for simulations. So that if you go for simulation, you need not have to make physical system. You will just go for simulation, and by simulating, you will come to know that that particular design is okay or not. Then after simulation, if simulation is not okay, you will go back and you will just correct whatever things you have designed. And if till that design is working okay, so many versions will be there. After making that, after doing simulation and checking the simulation, and if you find that everything is okay, simulation is okay, then you will go for layout. Layout, mostly everybody is familiar. Layout is done in a fabrication lab. Layout. 2-3 things are there. One thing is simulation. Simulation, you can do simulation of layout also. Analog electronics, analog layout, you can do simulation. Digital simulation also you can do. So digital simulation, that is if you have done VHDL or if you have done Verilog, and VHDL and Verilog, you made any digital IC. So you can do by simulation, you will come to know that particular IC, how to test, how you are able to make the function, basic function of that particular IC, and then you can check by simulation. So once simulation is ready, you will go for layout. Making layout means, as you know, making layout means then you have to go for DRC check, design rule check. Design rule check means lambda length and what will be the size of the pattern, what will be the size of gate, what will be the size of drain area, source area. So all those things you will check by design rule check. If designs are as per requirement, is okay. One more thing. When you make a layout, before making a layout, you will have to contact a particular fabrication lab like SCL, Semiconductor Complex Limited. You have to take technology file from Semiconductor Complex Limited, and that technology file you will have to use in your layout. So once you make technology file, that technology file will be used for making layout. Okay, if you are making by Indian foundry, it is okay, SCL will be useful. If you want to make lower dimensions, 20 nanometer, 40 nanometer, or 10 nanometer, then at present SCL does not have capability to make so small. SCL has capacity to make 18 nanometer. Okay, so layout is to be made after taking technology file from for the fabrication lab. So once fabrication lab has given technology file, you have taken technology file in your layout, you will check your layout with schematic. In VLSI, one important thing is there, each steps are very, very critical. Okay, and if you just make a mistake, on a wafer, if some dust particle is there or a hair is there, in that case, that particular wafer will not work if you make the IC. So, in order to make foolproof system, you will check after doing any operation, you will do check. If you made oxidation, you will check whether your oxidation is okay or not. If you make metallization, you will have to check whether your metallization things and your functional things are matching or not. If I make a layout, then I will layout of a particular part. Then I will have to see that this particular part layout is working as per function. So we will do layout versus schematic. The function of the layout and the schematic, they should match. Then we can proceed. And then after making LDS, we will do parasitic extraction. Parasitic extraction means so many things are there. If you are making some design, generally when we do a design, in that case, we will just see that some abstract parasitic should be extracted. Delay should be seen. Delay will be, if delay is there, you should effect of delay you have to account. So that if some RC component is there, so what will be the delay? If some resistive component is there, what will be the delay? So that parasitic extraction, actual design and simulation design. Simulation design will not have a parasitic extracted, but actual, if you are trying to reproduce the actual thing, in that case, you will have to go for parasitic extraction. And parasitic extraction, you will come to know that if I use this particular part of the circuit, in that case, my delays will be like that. Most of the time, if you just account for the delay, if your design account for the delay, in that case, whatever design you make on the circuit, that design will work when you make complete layout circuit. If you do not do some practical things, you have to extract and you have to find out. If you include all those things, in that case, whatever actual design and whatever simulated design, if you just insert the parasitic, in that case, that will match. So, whatever things you make mostly will work in little efforts. Okay, next. Okay, the design process. When you make a design, you have to start with the specification. What will be the total, how many transistors are there, then what kind of transistors is there, and whether transistors or the circuit diagrams layout is available, design is available. So you have to see the library, your library. In the library, some Engg gate library, other library that you have to see. And after, if you get library, so whatever functions are available in library, you should take it and you should use those functions from the library. Then you will do synthesis. Synthesis is opposite of analysis. Analysis is different, synthesis is different, but they are opposite. So when you are making a particular design, in that case, you will first see synthesis. Synthesis means you will extract the function. Then are so many logic synthesis. If we are making some digital design, logic synthesis, circuit design, layout generation, you will do. Then sequential synthesis, you will do. If you are making a digital design, all those things you will do. Then you will do design analysis, property verification. How many gates are there and how much time it will take. So you have to do verification. Verification is a very tedious thing in digital. And if you are making a design with millions of transistors, and if you do not check it, if you do not verify, then it is always possible that that particular IC, that particular design will not work. So that thing you will check by doing verification. Verification is bottleneck. You have to use some EDA tool for doing verification. Constant satisfaction for the cost. Okay, then you have to see that, okay, I am going to pay this much cost, so whether whatever things required by me, all those things are meeting or not. So you will have to, then that is one constant, your cost. that, okay, I'm not going to use these particular things because of cost. So you will have to first find out. Then cost is one factor, performance. Performance, we want to make the layout and other things, then we'll have to see its performance. How much power is there? How much test? When I'm making a particular design, then you will have to see that whether that particular design is possible to test or not. If you are not able to test the design, then there is no sense. So you will have to see that design for testability. You will have to introduce some test point, and you will have to see the function. Then and then only you can say that no, my design is okay. Okay. Then after doing all those things, testability, manufacturing, other metrics, other things, then documentation. Documentation is very, very important. If you are, otherwise, what will happen? If you make something and if you do not do documentation, after 3 months, after 6 months, if you again work on that, you will not be able to recall. So documentation is very, very important. Documentation is proper. In that case, you can just extract the things after some time. Manufacturing means whether you will be able to manufacture this particular IC, all those things. Next slide. Okay, design, capture and modeling. You will have to do modeling also. Simulation and modeling. Modeling in a hardware description language. All of you are familiar with VHDL Verilog? So that is a modeling language actually. Hardware design, VHDL and Verilog. And you should, if you are working on a digital design, then you will have to see logic synthesis, whether you are able to synthesize the logic. Then sequential synthesis. Sequential synthesis means if you are able to make if suppose you are using a particular language, say C language. C language is a sequential language. Okay, VHDL and Verilog, they are concurrent language. So those things you will have to see. Then after doing some synthesis, higher level synthesis you have done, system synthesis you have done, then you will have to see verification and simulation. Verification, complete function. If you make a microcomputer, if you make a microprocessor, and if you are not able to find out, you are not able to simulate, you are not able to check whether whatever things you have done, that is okay or not. So that thing you have to assure that how many transistors and circuits are there. You will have to just do simulation, and you have to verify whatever design I want. I should verify that that particular design is okay or not. So in VLSI, testing is very important. If you are failing in one particular part somewhere, in that case, complete VLSI design will be in problem. So that thing, verification you have to see. And so many verification tools are there. With that you can verify. Like in microprocessor, microcomputer, logic analyzer is there. So with that you can just check the design, verification and simulation. Then physical design. You are putting millions of transistors and you are making layout for millions of transistors. You have to use automatic tools. Cadence, synopsis, mental graphics and other tools. So those things, how to do placement. Whatever silicon area you are having, in that case, how much space you are properly utilizing. So that part you will have to check in physical design. Routing you will have to do how to route the connections, patterns, so that the silicon area is minimum. And then after that, the most important part is testing. Whatever testing you want, that thing you will do. Next slide. Okay, SoC characteristics we have seen. What is SoC? System on chip. VLSI manufacturing technology advances has made possible to put millions of transistors on a single die. It enables designers to put systems on chip. One silicon will be there, and analog, digital, microprocessor, microcomputer, everything things you put on a system. So nowadays that thing is going on. So many system on chip SoCs, ICs are available. In that case, what you do, you just program it. If you want some design RAM, you will program the RAM and you will put it. So that things are available. So SoC is system on chip that move everything from the board onto chip. I will show one or two slides. In that case, you will get a picture of a board What is board? Then how to make board on system on chip. SoC not only chip but more on system. SoC chip plus software plus integration. That is SoC. SoC chip includes embedded processor, ASIC logics. Okay, embedded memory. Embedded is one. Everything is one. Okay, SoC software will be operating system, compiler, simulator, firmware, driver, protocol, stack, interior. All those things will be there in SoC software. Okay, nowadays, if you make a SoC, you will have to use so many capabilities of a computer that with that you will make system on chip. System on chip integration includes whole system solution, manufacturer, consultant, technical supporting. SoC chip is where when integration level is higher than normally in practice only, one chip can contain all logic needed for one equipment. That thing is SoC. If your design is very cumbersome, design is there, you will try to put on a single chip. So system on chip. It is one chip embedded system. Embedded means one stone, everything is included. So SoC one chip embedded system. Current high density chip manufacturing process make it possible to have a large number of logic gates on one chip. SoC can be application specific standard product, or most often SoC is ASIC, system on chip, everything. Analog, digital, microprocessor, microcomputer, memories, processors, everything on that thing, and that is system on chip. Nowadays, system on chip concept is coming very fast. Next slide. Benefits and drawbacks. Okay, that is one thing. Here, so many system on boards. Have you seen some system on board? Some slots will be there, and slot will be inserted, and that particular board working capability will come. System on board, so many boards are there. Now all these boards are replaced and they are put on a single silicon. Whatever functions you will have on board, that function, and so many boards are there. So complete boards functions you are putting on one silicon, and that is system on silicon. You can call it system on chip. I will just say that system on silicon because in microprocessor, microcomputer, so many digital memories, digital controller, digital processor, all those things will be there. So system on silicon. So that thing will be there. Top level design, so many alternatives you will have to follow. Top level design you will do, and then after that you will have to verify the function. Always it is advantageous to make things in small. One particular things you make one module, another things you make one module, another things you make one module. And in that case, so that you will be able to test that particular module efficiency. You will be able to find out where is the problem. Otherwise, everything you will make in thing, and if you want to just check, in that case, where problem is there, it will not be possible. So better you make in design is modular, and then you check whether that particular design is working or not. Okay. Integration and synthesis, trial netlist, timing, convergence, verification, need to reduce time before vendor steps, need to consider layout issues up front, and then design versus testing, and then time to mask, making a mask for that, and then checking. Okay, next slide. General SoC, CPU, then device, modular they have made, CPU is one thing, and then so many devices. That thing is system on chip, peripheral device and other things. Next, system on chip course, that thing will be macros, cores and cells, that will be done. And blocks can either be developed in-house, licensed from IP company, all those things will be done. Okay, soft core, firm core, hard core. Soft core, it can change. If you make in software core, in that case, later on, if needed, you can just change the software. And you can just change the software, and with that, you will get back the required things. Firm core, software and hardware in between. Firm core, some things you can change, some things you cannot change. And then hardcore, hardware. Hardcore, it means that you cannot change something. You cannot hardcore. Whatever things are there, they are frozen, they are fixed. You cannot check. Okay, so next slide. Then locating the required cores and associated contract discussions can be lengthy process. So if you are making a particular ASIC or if you are making a design, you will have to find that this particular small module is available by some particular vendors, IP vendors. IP vendors is intellectual property things. In that case, when if you are making complex things, you will have to find out whether such small module is available as an IP core or not. If they are available, then there is no point in repeating all those things and making again. So if IP cores are available, in that case, just you find out and you just pay the royalty to the IP core vendors, then you can just take that particular function, and after taking that function, you will start using remaining part, and then you can just do. Evaluation criteria. What is the criteria? That thing you will have to find out. Comparative evaluation exercise you will have to do. Then choice of core. One more thing is that choice of core means, suppose if you are making a particular things, in that case you find out whether, suppose for example delay, if that delay is available by making hardware, in that case you make that thing, or if that particular delay you can just simulate through software, then you should find out whether I should take a decision whether to go for hardware delay or whether to go software delay. If you want to go for hardware delay, and when you integrate, in that case, that will be the faster. If something you are doing with hardware, that then its performance will be faster. If something you are making with software, delay is making software, then in that case, particular part of that software will be used. So that cannot be very fast. Software delays will be there. So that compromise you will have to do. Then all those things you will have to do, and core integration, simulation and verification you will have to do. Okay, next slide. Benefits. Lower cost per gate. If you make a system on chip, lower cost per gate, lower power consumption. Do you know what is power consumption of a CMOS IC? Power consumption CMOS IC? Yes. हाँ वो होता है. CMOS power dissipation is very small. बाकी TTL power dissipation is very, very large. Then you want lower power consumption, then you will go for CMOS technology. And so many other criteria are there by which you can just reduce the power dissipation. So that you will have to follow. More reliable implementation. How you will do? Suppose if you are making a particular design with some particular modules, in that case you will have to see there whether that particular module is reliable or not. If it is not reliable, then you should not use it. So reliability part also we'll have to see, and we'll have to just implement by reliable things. Smaller physical size, greater design security. Design security should also be very important. More functionality in one-time manufacturing cost, inexpensive solution in large quantities, near completed or partly solution available, IP and intellectual property. Cheap is just what is wanted, no more, no less. Whatever you want, enough. It should not be reduced further, or you should not extend more things in that. जो बना लिया आपने वो sufficient है तो वही रखना है, फिर ऐसा नहीं हो कि थोड़ा बढ़ा दिया फिर वो उसमें भी बहुत दिक्कत होती है. Next slide. Drawbacks. Principal drawbacks of SoC design are associated with the design pressures. Time to market, very important. Okay, if you are making a particular design, if you make a design and your idea is to just sell, you are just making a particular design as a project, and that particular project you want to launch in the market. So you will have to see whether if you make that particular project now, then you will get the advantage of market. But if that same project, if you make after some time, in that case, by that much time, you will lose that thing actually, because you are not made in time. Some other company has made it in time. So you will not be able to get the advantage. So that thing is very important. Okay. Huge cost, tools, ASICs, NRE, costly IP, risk of chip, all those things you will have to see. Whatever things you are making, in that case, whether your cost is okay, sufficient or not. Okay. Next slide. Solution. Okay, one more, next slide. This thing is there. the outer green things is, if you start the design from the origin, that thing, you will get that much time to market. But if you design late, a small circle, dark green, small circle, if you design the design is late, if you introduce the product in less design, in that case, it will get only this much time to market the price. So you will lose. You will not be able to go to peak. You will just go to some peak, lower peak, and then you will be able to lose that thing. So you will have to see the market window, peak revenue. How much peak revenue you will get if you just introduce that particular design. Okay, next slide. Gates per design. You will have to see how many gates per chip. If you got large number of gates per chip, that is one thing. And design productivity gap. If the productivity gap is more, in that case, your design will be late. Design will be introduced late. Okay. Then gates, you will have to see gates per hour. How much gates you are able to make, and cost. Suppose if you want to make the cost estimate of your design, in that case, how you will make it? You will see that how many engineers you have employed, and you will what salary we are going to engineers, and how much time they are taking to design that thing. So with that, actually, cost is calculated. And if you make large number of gates, in that case, cost will be more and time will be more. Next slide. This picture shows so many PCBs interconnected, wired, and other things. This is the story when I was a student. Then in that case, because system on chip was not there at the time. So making one particular part of circuit on one card, another card, and these cards will be interconnected so that complete system function will get. So things become very complex. Some logic analyzer or some equipment, oscilloscopes or equipments are there. With that, you used to test connecting the probes, so many points probes, and then you will have to test whether this particular part is working properly or not. So all those things you will check. Next. Now all those things, so many PCBs, all those things now we are making on particular silicon chip. That is FPGA, RAM, 32 KB of RAM. That module is available. RAM will be integrated with FPGA. Then microprocessor, bidirectional bus is shown. Microprocessor is integrated with FPGA. Microprocessor is implemented with FPAA. What is full form of FPAA? Anybody knows? गेट अरे गेट है ना, ठीक है. और FPGA तो मालूम है आपको, वही है ना, वो है. तो ये चीज है, ये structure of a mixed signal development. This is a mixed design. Mixed design means something which is there in the front, something which is there outside. So all those things are integrated, and then particular mixed signal circuits are made. Okay, next slide. Okay, this is the case. Prototype, some companies are making system on chip. So they are making system on chip, and they provide some connectors and other things. So proper circuits you can just connect to them, and that particular things will work as a system on chip. And this is a prototype. Prototype is suppose today I make one design and I test that design. Later on I will find that no, I have to change my design. So system on chip will provide you. You can just change your design. Either you can change by software or you can change by hardware. So that complete things you should be able to find out. Power PC, prototype board with LCD screen, USB ports, Ethernet and other connectors. So they are reconfigurable SoC. They are not fixed SoC, reconfigurable. Later on, once you do design, once your work is over, in that case you just reprogram to make another function, and you can just test that particular function. Okay. Next slide. Fast prototyping is very important. Nowadays, you will also find that so many companies are making some particular product. Okay. So normally these companies, they want to do design on FPGA or FPA. What are all the advantages? FPGA, FPA advantage of making design. In that case, you can just make in typical stages, you can make on particular things. You can just change it. So mixed signal circuit design having analog, digital and processor, mixed signal circuit design. Then consolidation of analog and digital part, validation of the design, very important. You have to validate the design. If design is not working, repeat execution of steps 1, 2 and 3. Resources for fast prototyping, analog and digital circuits. APA, field program, and analog part you can just make by APA. So that is not fixed. You can just change. Op-amp, if some op-amps are there in APA, you can just making programming, you can just change the connection. So that particular things will make some other function. So validation of the design, you will have to test that design, you will have to see that whatever function you want, whether that function economically properly is available. If design is if design is not working, repeat execution of steps 1 and 2, 3. You can use APA or APG, or you can use both. APA and APG is on the same thing. Rapid prototyping. Companies, those who are working on these fields, so they will not wait to make that particular fabrication thing. Do you know? Suppose if I want to fabricate IC, in that case, how much cost will be there and how much time will be there? As far as cost is concerned, about $10,000 or $30,000 will be required in making particular IC, and about 2 to 3 months will be time consumed by making that particular IC. So you just know, if I make a IC, shall I go for fabrication? Fabrication, if I go, it will take 2 to 3 months. It will cost $20,000 or that thing. So I have to decide now whether to go for fabrication or not. In fabrication, if some a previous stage, if some problem is there, some hairline, some design, hairline impurities, other things are there on that particular wafer, in that case, that design will not work. So whether to go for fabric. So mostly companies are not going that thing unless they are sure, unless they have done repeatedly, they have tested that particular design. They will go for prototyping. They will go for FPGA. They will make the complete digital circuit on FPGA. They will make complete analog circuit on FPGA, and they will just make the complete system by that. So that testing FPGA is very small, very short. You can just design complete thing on FPGA. FPGA very cost. So rapidly you can just find out, okay, this is my IC working on FPGA, FPGA. Okay, so with that you can check. Resources for fast prototyping, analog and digital circuits, FPA and FPGA. Okay, next. Okay, this is a board, mixed signal board. Everything will be available here. Analog will be, some IC will be there for analog, some IC will be there for digital, some IC will be there for processor, microcontroller, microprocessor, and like this board will be there. So this is one option. You can develop your system by using these things. Next. Okay, this is again rapid prototyping. Individual modules are available. ADC, analog to digital converter available. FPGA, programmable gate array. FPGA, programmable gate available. Amplifier, filter, all those things are available. So you will just insert in proper slot of a system on chip, and then you can realize your design by these particular things. Okay. Next slide. Okay, same thing is programmable SoC. Cypress Semiconductor has introduced this one. So rapid this IC SoC is available by Cypress Computer. So you can just, whatever modules are available, just realize those modules, interconnect them, and just get the function of your system. Next slide. You can just make intellectual property. Everybody is familiar. No? So it is always very beneficiary if you proceed by IP. Whatever things are available, use those things. You need not have to spend same things again. That will take more time. You will become late. So whatever things are available, just purchase from paying royalty, make that thing, and proceed for design this one. Okay, IP blocks are sold as one-time payment or license. Okay, next. Okay, that design IP core. IP authors, the producers रहते हैं उनको payment करो आप उसके charges royalty and use that IP. So with this, if you proceed, in that case, your design of that particular function will be faster. You need not have to always make everything from scratch. They are available. Okay, next slide. Okay, SoC application. So it is there in communication, microprocessor, microcomputer, codec, Bluetooth controller, timer 1, timer 2, PLL, UART, all those things are there. So they are the application of SoC. Nowadays, SoC is very popular. Okay, next slide. Okay, SoC is used for speech signal processing, image and video signal processing, information technologies, PC interface, data communication, wireline communication, so many 10, 100 base and DSL, gigabit, Ethernet, etc. Wireless communication, Bluetooth, wireline, 3G, 3G, 4G, and so many things are advancement have come. So these are applications of SoC. Okay, next. Okay, summary. Technological advances mean that complete system can now be implemented on a single chip. Okay, we use multiple design capabilities, architectural design with software, firmware IPs, hardware IP, software IP to create new platforms. Integration requires the use of multiple design flows. Good tools are needed to address SoC. Good tools are needed. If you don't have a tool, you will not be able to verify the design. So that good tool like logic analyzer, development system, with that very quickly you will be able to debug the problem. Drawbacks are that systems are extremely complex, requiring amounts of verification. Bottleneck verifications is very important. Otherwise, making a microprocessor and checking that microprocessor is very important. Bottleneck. Avoidance of silicon, deep submicron effects, area, power, performance, embedded code optimization you will have to do, verification you will have to do, testing you will have to do. Then only you can say that, okay, my product is operational. You can deliver it to some customer. Okay, next slide. Okay, thank you. Okay, if you got any doubt. Kuch doubt or
Anyone having any question related to the SoC? You may ask.
Anybody, any questions are?
Because somebody is doing the PhD in the relay side field. Name, sir?
For sharing your knowledge and insight as today, I request Dr. Amiteshwar Bhalavi sir to honor our chief guest Dr. Deepak Kumar Mishra sir to token of remembrance.
Thank you.